Welcome, I'm Doris Israeli, a team leader at Quantum Machines, and today I'm going to present the Fullstack Quantum Compilation Challenge, mining the pulse gap. So let's get started. In Quantum Machines, we developed the Quantum Orchestration Platform, or the QP as we call it internally. The QP on the one end lets you control the qubits or physical system using RF or microwave pulses. This is done through our pulse processor, a dedicated chip that controls the qubits and allows you to generate waveforms in real time, to measure the qubits by acquiring those waveforms. It allows you to evaluate functions in real time, in mathematical and arithmetical functions, and also it has a support for control flow like while loops and conditions. This is natively enabled for all of the qubits and exposed via our pulse level language, which is QA. QA is an open source language that we have developed in the past 3 years. It gives the user a very high level, an intuitive one, pulse level control of the system, and allows the user to focus on the intent, on the algorithm, instead of the hardware constraints. Under the hood, there's the QA compiler that figures out how to handle all of the instructions, and through that integrated hardware and software solution, QA enables the QOP to control all types of qubits. We have almost 100 customers all around the world with superconducting and cold atoms and trapped ions and so on. This is the Quantum Orchestration Platform, or QOP. So our customers use the QOP for all kinds of applications. Some use it for general research. Some use it for characterization calibrations, right? Some use the QOP for quantum sensing to build better sensors. Some use it for quantum communication even. And recently we demonstrated quantum error correction schemes using our QOP. Today I'm going to talk about quantum computing algorithms. We've implemented several quantum algorithms, for example, QAOA, randomized benchmarking, cross-entropy benchmarking, and some more. And this is great, but we implemented all of those in the pulse level language. Some of the implementations has merit to be implemented in pulse level, in the low level, right? But we want to enable our users to reason about quantum algorithms in their native language, which is the circuit model languages. So let's talk a bit about what is the circuit model. So the circuit model is the computational model for quantum computers, right? So in classical computers, we have the Turing machine. In quantum computers, we have the analogy of quantum Turing machine, but we also have the equivalent circuit model computational model, which is a bit more appealing, and let's talk about why. The circuit model, to begin with, is an abstraction, right? We have qubits, they don't disappear, they are not added throughout the experiment or the algorithm. It's very visual, right? As you can see here in the screen. And it's implemented in gate level languages, for example, Qiskit by IBM or Cirq by Google. The operations you can do are simply gates, for example, the Hadamard gate, or measurements, usually in the end of the circuit. The only constraint that you have is that you cannot apply two gates or two operations, let's call it that, simultaneously. So for example, here in the circuit, in the example, we have an Hadamard gate in the beginning, right? So you cannot apply another gate, let's say an X gate, simultaneously. It has to be applied before or after. That's it, right? So it allows us to focus on the mathematics, on the algorithm, on the intent. It's hardware agnostic, meaning we don't take into account the QPU types, the hardware system, right? The control. We don't concern ourselves with time, right? It's time agnostic. So we don't have the notion of time. What is the duration of a gate? What happens between gates? We don't think about that. And these abstractions makes this computational model more very appealing, right? And we want to allow the users, we want to allow our customers to reason about quantum algorithms and integrate with the higher stack of languages and libraries that exist in the ecosystem, right? And we want to support all of the QPU architectures like we do today. We have customers doing superconducting and we have customers doing photonics even, right? So we want to allow them to take some quantum algorithm, specify or configure their specific setups, because one customer's setup is not exactly like the one next to it. And our QOP solution will find a way to control the qubits via pulses. This requires a gate level to pulse level compilation. Compilation, I mean a few things, but why is it required? So let's talk about quantum compilation. The first reason we need quantum compilation is simply functionality, right? So the hardware doesn't understand our mathematical abstractions, right? Gates and circuits are in the end some mathematical construct that is easier for us as humans to reason with, but the hardware in the end works with pulses and instructions. The second reason is the optimization, right? The optimization is the act of taking one circuit and making it better in some manner, usually in the number of gates or the number of 2-qubit gates, or in the depth, right? Or in the fidelity of the computation. And this is nice in general, but specifically for NISQ, for the NISQ era, for the short-lived qubits with the low fidelity, which is the era we currently live in, it's a must. And it's a tough problem, right? There are companies doing specifically optimization or even sub-problems in optimizations. So let's talk about those challenges. We usually separate the challenges to two groups. The first one, which are hardware agnostic, and later on, the hardware dependent ones. So let's begin. To begin with, you have some problem at hand that you want to solve, for example, some equation, right? It could be a mathematical one, it could be some physics problem, an Hamiltonian, for example. You want to synthesize a circuit, okay, out of this mathematical problem, such that a quantum computer could solve. And then this circuit should be optimized, right? Maybe it's very long. So you want to make it better, to improve it, again, by some benchmarks. And again, this is a tough problem. Now, both of these steps are hardware agnostic, meaning we didn't concern ourselves about the control hardware and the qubits. Now, when we want to execute this circuit, we gotta make a few passes that are hardware aware or hardware dependent. The first one is to lower the gates to the natively supported gates. Maybe I have in my circuit now the Hadamard gate, but my QPU doesn't support Hadamard, it supports a rotation, right? So we need to convert the circuit into the natively supported gates circuit. Then maybe the gate depth was harmed in the process, so we want to optimize again. This is great, but it's not the end. Algorithms are written or are using qubits, the logical qubits, the virtual qubits, the concept of qubits, but in the end we need to specify which qubits should be allocated. Okay, this step needs to take into account the connectivity of the qubits. Today, and most evidently in superconducting QPUs, not all of the qubits are connected. So if, for example, I want to do a 2 qubits operation on 2 qubits and they are not connected, it's a problem. I need to somehow route the qubits to be connected. This involves in adding more swap gates into the circuit, thus harming the fidelity. This is a tough problem. It's mathematically speaking, it's NP-hard, right? And even now we are not done. So once we have allocated the physical qubits to the virtual qubits, now we need to schedule the gates. So each gate, in reality, each gate has some duration. Some are small, some are longer, right? Maybe different gates on the same qubit have different durations, or the same gate or different qubits have different durations. So we need to schedule the gates relatively to each other. Then the final step is to translate or to lower the gates into their equivalent pulses. And one gate, for example, could have multiple pulses playing to different parts of the system. Those are the challenges, and they are tough, right? But once we solve it, once we solve all of those, compilation steps, we are golden, right? So yes and no. Yes, for toy problems or for very naive approaches, that's okay. But it's not enough for next-gen quantum programs. And I'm going to give you a few examples, and I hope to convince you that it's not enough. So let's begin with an example that most of you know. I guess most of the people that learn quantum computation see the quantum teleportation circuit relatively in the beginning. Here in this problem, we want to transfer some information from one qubit to a different qubit. Okay, We won't go into detail as to why it works, right? But let's look at the circuit. In the beginning, we have a CNOT gate and a Hadamard gate, which are cool. And again, don't break the circuit model. And then we have mid-circuit measurements and mid-circuit real-time conditionals. If that qubit was in the excited state, if it was 1, do a Z gate or do an X gate. Why is this problematic? That is problematic because the target qubit, which the information is going to be passed into, should stay alive in the process. And qubits, again, most of the qubits are short-lived. Okay? So that means we need to enrich the circuit model and the hardwares and the languages with mid-circuit measurements and conditions. Mid-circuit measurement is not strictly not enabled in the circuit model, right? But it's not supported by almost all of the platforms today. Now, a different example, the reset operation. So a lot of quantum algorithms assume the qubits start in some state, for example, the relaxation state, the zero state, right? The ground state. And some algorithms even use this operation in the middle of the circuit, and I'll give an example shortly. One naive way to achieve this operation is to just wait for time which is longer than the relaxation time, and then the qubit will probably be in the ground state. This is not good for several reasons. The first one, obviously, it's a statistical number, right? If I waited for t1 nanoseconds, that doesn't mean that the state of the qubit is the ground state. Secondly, in the circuit model, as we've mentioned earlier, we are time agnostic, so it breaks the abstraction. And thirdly, it's not efficient, right? T1 could be very long, or even if you want to be more certain of your reset operation, then you will wait for, I don't know, 10 T1s, right? It's not efficient. So maybe a more efficient solution is to add mid-circuit measurements and real-time conditionals and do something like that. Measure the qubit. If it's excited, then apply an X gate on the qubit. Otherwise, apply the identity. Just wait. Don't affect the qubit, right? It's already in the desired state. And this is great, other than the fact that it shows us again that we need the mid-circuit measurements and the conditions. But yet again, it assumes that the X gate is flawless, but it's usually has some non-100% fidelity, right? So we want to do that maybe again and again and again indefinitely until we have success, right? So now we want to have some while loop. While the qubit is excited, right? Do an X gate and measure it again and again and again. Repeat that process. So now we need while loops, and that adds more issues because now the reset operation, the duration of the reset operation is non-deterministic, right? How do we schedule the pulses if we don't know when the reset operation ended? A more advanced and recent example is by Honeywell from last year. This scheme is about active error correction, or more exactly, as they coined it, adaptive error correction. And I won't go into too much into detail, but if you zoom in on the part that I've highlighted, we can see they have mid-circuit measurements, right? And then a condition. And what is the condition? The condition is to check whether the syndrome has changed. That means that not only do I measure the syndrome, I need to keep track of the syndrome. So now I need also memory. And that's not enough. I'm going to differentiate the states, right? I want to see if there was a change. So I need real-time logic, real-time arithmetics, maybe. And then according to the result of the condition, I want to play a circuit, either the right one or the bottom one. And they have different durations. So how do I schedule that? Once again, we get to the conclusion that we want more features, right? That the circuit model, the naive circuit model, doesn't have the naive, the current state of platforms don't have, for example, Qiskit. And this was coined by IBM as dynamic circuits. Dynamic circuits are circuits with feedback, with mid-circuit measurements, with real-time operations, and an attempt to formalize those circuits and to give us a way to reason about those kinds of circuits is OpenQASM. OpenQASM 3 is an open project intermediate representation language led by IBM, but again, it's an open project, so the steering committee has representatives from Amazon, AWS, and from more companies like Microsoft and universities. It's an attempt to formalize both the most abstract circuits with the high-level imperatives that we've recently talked about, the mid-circuit measurements, loops, right, variables, down to the most physical circuit with timing and with respect to timing or physical qubits, right? This is the future. This will become the go-to reasoning for Qiskit for sure, right? Because it's led by IBM, and I'm sure more will follow as most of the industry today adopted the previous version, OpenQASM 2. So this is an example. I'm not going to go into detail as to why this algorithm works, but this is an example from IBM's paper from last year about dynamic circuits, and an example for an algorithm called iterative quantum phase estimation, which shows that if you have the reset operation and mid-circuit measurements and real-time logic, right, then you can achieve the same results as a naive circuit will achieve with less qubits, for example. Okay, this is the OpenQASM 3 code required to implement that, and again, it's open source, so you can just look it up in the repository. It's a work in progress. I actually lead one of the working groups, and we're quite involved in OpenQASM 3. And in this code in red, as I've highlighted, you can see real-time variables, the reset operation, for loops, okay, mid-circuit measurements, real-time calculations, right? And we need to support that. We need to enable all of those rich features, both in the languages and the underlying software and in the hardware foundations. We need to enable that. And it has a lot of implications, right? All of those features and new constructs, they add new compilation challenges that we haven't faced before in the quantum industry. Now, the program is not just a linear flow of gates, right? One of the most appealing features of the circuit model was that it's visual. This is the circuit, right? And you just pass each of the gates. Now we have basic blocks. We have conditions, right? The program is not linear anymore. Now we have loops. If we have loops, we need to optimize the loops, right? This is a challenge that we've already faced in the classical programming languages, but now it encounters the quantum operations. How do we settle the disagreements that arise? If you say we don't need loops, let's just unfold all of the loops, right? You get a blow up in the number of instructions. For example, the Hadamard, the quantum Fourier transforms uses 2 loops. So it becomes quadratically longer. And also, these next generation quantum languages gives rise to new quantum specific challenges. For example, the classical logic latency. So classical imperatives, for example, conditions, have latency, right? The condition needs to evaluate the condition and then branch according to the result of the evaluation, right? And that takes time. Now, we don't think about that in classical programming, but in quantum programming, this time may create a gap in the pulses, and that gap may harm the fidelity. So we need somehow to take that into account in our underlying foundations, to make our compilations aware to this fact, to maybe execute some of the calculations and pulses together. Maybe we need to do some new hardware developments for that. And I want to show you 3 short examples. For example, I want to apply the X gate on qubit number 0, and then I want to calculate some cosine, and according to the result, I want to play some rotation, right? There's no logic, there's no sense behind those examples, just to show you that the gaps might be very evident. So, for example, the cosine evaluation takes time. Now you will have a gap between the X gate and the rotation gate, right? You would somehow maybe want to parallelize the computation and the X gate, maybe even push the cosine using constant propagation to push it back. Another example is that you want to measure a qubit and then another one, and according to the result, if they're both excited, do an X gate on the third qubit. The condition takes time, right? So the measurements obviously can happen in parallel, but the condition needs to firstly check that both of the conditions are true, and then if so, branch or not branch according to the result, right? And that takes time and cycles of the underlying processing unit. How can we mitigate that? Can we mitigate that? Even in loops, if we want to sweep over some parameter, that means that we need to increment, for example, the parameter, and we want to check that we don't go overboard, right? We're not overflowing from the upper limit, for example. That takes time. We need to take that into account, and QA tries to take that into account. QA handles that. QA both enable the high-level functionalities that we need in the next-gen languages, and also allows you to have some control over the timing imperatives. So obviously, because it's a pulse-level language, we have the play and measure commands that plays a pulse and measure requires some other channel. Then we have real-time variables and real-time calculations. So for example, you could say a variable in real time equals to b, maybe b as a result of a feedback, okay, squared, and you can calculate square root and cosine and whatever you want. We have that. We could even use those real-time calculations and variables in dynamic plays. Here you can see the pi pulse amplified and stretched out, and we can even change the frequency, right, and truncate maybe the pulse. We can have very advanced measurement schemes, right? So we can acquire some channels, some qubit, and then do some smart integration, again, all in real time, right? And then through some mathematical algorithm, for example, a simple threshold, maybe even machine learning, or there was a recent paper about using SVM to do state discrimination. We can discriminate whether it was excited or in the ground state. We have full control flow, right? We have conditions and we have loops, okay? And we gotta have that to enable the control flow imperatives, for example, in OpenQASM 3. Also, and finally, we have timing control, both absolute and relative timing control. We try to focus on NISQ applications, right? For example, you want to do multiple shots of the same circuit because, again, quantum algorithms are statistical, right? You want to maybe rerun the same circuit multiple times. Maybe you want to rerun the same circuit but with different parameters. Your hardware and software need to take that into account. You need to support long programs, right? So every hardware has its limit, and if the limit is longer, the better, right? I want to focus on two examples. Let's begin with pulse level error mitigation. Because we give a rich pulse level control, we can enable very advanced and very accurate and very fast schemes. So for example, error mitigation is a technique that tries to mitigate errors, not to solve all of the errors like in fault-tolerant quantum computing. So it's very relevant to the NISQ era. An example for error mitigation is the zero noise extrapolation that says the following. We have some noise in our circuit, okay? Because of many reasons. Maybe we can add some noise and add some more noise and some more noise, and then in post-processing, extrapolate back to the state of zero noise, for example. That's a really beautiful idea. And on the bottom left, you can see the drawing, the schematics from the paper from Candela and J Gambetta that stretch out pulses and amplify the gates and so on. And again, we don't have that in the circuit model. We don't have this kind of control in the circuit model. And for example, Unitary Fund, which is a great non-profit organization that strives to enable and develop open source quantum software, they developed MITIC. MITIC is a gate level error mitigation compiler that uses, for example, zero noise extrapolation. How do they implement that? They add gates as the noise source, right? Because they are not exposed through the circuit model to the pulses, to the control of the pulses. So maybe we can implement some error mitigation schemes in pulse level, and QA, our pulse level language, enables that. Another example is pulse parameterization. So a lot of NISQ algorithms, for example, VQAs, like VQE or QAOA, optimize some parameter which affects the rotation angles, right? And that's it. That's all you can play with, the angle of the rotation gates. But under the hood, in the pulse level, we have so much more freedom. We can change and parameterize the pulse amplitude and duration and frequencies, right? And that adds more dimensions to the solution space. Maybe we can implement some of those algorithms, or algorithms that are inspired from those algorithms in pulse level, right? In summary, in the future, the next-gen applications require real-time logic. They require variables. They require mid-circuit measurements and condition and loops, and who knows what's next. So our foundations, our languages and software and hardware must support real-time logic, right? Secondly, the quantum field, and pun not intended, is ever-changing. It's evolving all of the time. Every day we have this new paper by some lab that shows that if you have this and that features, then you have some advantage of some sort, right? We need to have the agility as a core principle in our foundation, right? If OpenQASM 3, which is, again, a work in progress language, adds another feature, we need to support that, right? Finally, we have a lot of applications in the quantum industry, from quantum computation to quantum sensing and communication, and so forth and so on. We need an efficient one-stop solution. We cannot have 10 solutions. We cannot have different hardwares all cramped up in one laboratory. We need a solution which is general and efficient. So thank you very much. My name was Dor Israeli, and I'm available via email, dor@quantummachines.co.